once again to the discussion on performance-based design. We have started this discussion on performance-based design, and we are going to complete it in 4 parts. The first part we discussed where we looked at why performance-based design should be carried out or needs to be carried out. And then the second part is, what is performance-based design really? If we have established that this is something that we need, what is it? So today we are going to talk about what is performance-based design. And like I mentioned, we already finished the first part, and then we'll talk about this one today, and then we'll follow up with 2 more parts later. So performance is actually about doing something which is well defined, and we just look at how the final outcome is, and we don't really focus on conforming to some standards. Of course, there are going to be standards and ways to do this one also, but the focus, the end result or the end focus is on performance and not conformance. When we do conventional design, traditional design, we are always focusing on satisfying the code. And that is our objective. We are forgetting what the performance of the structure would really mean if we satisfy or we don't satisfy the code. We talked about that in the other talk. So this is all about performance, and it's less about conformance. And that, to me, is the basic difference between conventional and performance-based design. So let me give you an example which takes me back once again to a long time ago when I started the practice. At that time, a typical way to specify concrete was to write down the proportion of the concrete components, like for example, cement, sand, and aggregate. And when I used to write the specifications for the structure at that time, we would write, make the concrete in a ratio of 1:2:4. 1 part cement, 2 part sand, and 4 part aggregate. And we also would specify the water cement ratio of 0.6 or 0.5. And then the contractor is expected to follow that. And the engineers on the site would check those measures. And after that, that's it. So whether we get the concrete that we intend, we do not know. And secondly, the contractor did not have the responsibility to deliver a concrete of a certain strength. Rather, his responsibility was just to follow the specification that we wrote. And if he didn't get the strength, the contractor can easily come back and say, I don't know about that. I followed your specifications. This is what is called prescriptive-based specifications or specification-based design. But these days, as you know very well, when we specify concrete, we specify the strength. And we let the people who make the concrete deliver it of that strength. For example, we say we need a strength of 50 MPa. Then the company that delivers the concrete or makes the concrete, it is their responsibility to do the mix design, to find out how much cement they need, how much water they need, how to mix it, how to carry it, how to make sure that when it's delivered on the site, it will actually achieve that strength. And if they don't, the concrete is rejected, and if there's any cost, they have to bear that. So this is the difference between prescriptive and performance-based or way-based approach. And this is what the structural design is also looking at. Rather than saying that please do this, we are saying do whatever you need, give me this in the end. So that's what the performance-based design is all about. So prescriptive specifications basically constrained innovation. They limit everything. They say, okay, do this, cement is so much, concrete is so much, mix it like that, wash the aggregate, and all of that. They give into a lot of detail on how this should be done, but they do not guarantee or do not expect a certain performance in return. So the contractor doesn't have any way to improve anything or to economize or to optimize. But performance-based design says, okay, do whatever you need, just make sure that I get this concrete with these outcomes. So it leads to innovation. The contractor can innovate, they can add more material, develop new types of making. They don't have to follow how much slump in concrete is. They just have to make sure that the final product will be what is expected. So that's another main difference between prescription and performance, that performance basically helps people to innovate and not restrict innovation. Now let's come back to structures one more time. If you look at the structural design, there are several key things that we are looking at. And these are some of them, in fact, most of them. First one is stability. We want the structure to be stable. How do we define stability? How do we achieve it? Strength. This is more easy because a lot of the time the building codes and the specifications focus on strength quite a bit. So this is well understood. Deformation capability, less understood and less focused. Drift in case of tall buildings. Ductility, very important, but hard to measure. Energy dissipation, another indicator, which is actually a sum of many of the performance indicators put together, especially when it comes to earthquake or even for wind. And finally, motion perception. How does the structure move, whether people perceive it moving or they don't perceive it moving. So these are some of the things that we look at when we do the design. But the question is, how do we explicitly check them? How do we explicitly make sure that these things are within what is expected from the structure? So let's take that as the basis and move on to design decisions that should be linked to performance. How do we make decisions in design that will be linked to performance and to give us those 7 indicators that I mentioned? There has to be a way of doing that. Not simply saying that I'm following the code procedures or code specifications or code guidelines or zoning and whatnot. We have to be able to explicitly link that with each other. Earthquake was actually a catalyst for starting performance-based design in structural engineering. Many other disciplines use KPIs or key performance indicators or performance based approach even in management. Even if you're an employee in a company, they will have KPIs for you. They will expect you, these are the things that you need to do. Some companies, traditional companies, will say, okay, you have to spend 8 hours in an office and there is a clock to check in and check out. What do you do in 8 hours? It doesn't mean you can come to the office and do nothing for 8 hours and you say, I've completed my 8 hours of work and I have the check-in and check-out time. But that's not useful. What is useful is what is the output during those 8 hours. These days we know, especially in the current situation, people are allowed to work from anywhere. They're not expected to work certain hours. They're expected to complete a certain task. So they have a performance indicator. If they satisfy that, then they are acceptable. Similar is the case for earthquake as a catalyst. When we have earthquakes on the structures, we expect the structures not to fall down, not to be damaged, not to have catastrophic effects. So how do we ensure that? So performance-based design actually started, and now it has expanded to other fields also. So let's talk about the earthquake a little bit. Now, this is a very typical and a very well-known figure that you might have seen when we talk about performance-based design for earthquakes. What it shows is what is the expectation of the public or the client from an earthquake, during an earthquake, and after an earthquake. So the first one is, so these are the 4 typical levels that we call performance indicators. The first one is operational indicator, operational level. That means the building remains completely operational. Lights are on, everything is fine. Then one is immediate occupancy. That means if an earthquake strikes, and after all an event, whatever event that is, after that event is over, people have to come back and immediately occupy and start their work. They should not have to abandon or wait for anything. Maybe during the event they have to evacuate, but after that they come back and start work. So immediate occupancy, IO. Life safety, that means the structure may be damaged significantly, but lives will not be lost. That's another performance indicator. The structure should be designed in such a way that, okay, in a worst case, or the structure gets damaged, but the people's life is not lost. And because that is a concern, as I mentioned from the previous talk also, safety is one of the concerns. Although this is not sufficient, and we will talk about that when we talk about resilience-based design, which is another discussion altogether. And the last one is CP, collapse prevention. That the structure should not collapse even though it is heavily damaged. So in the second case, life safety, the structure can be repaired and retrofitted after the event and then become operational again, but in the last case it will just be gone. So that's the extreme event. So we have these stages or these performance expectations from a structure. how do we link them to earthquakes? How do we link them to design decisions? That's what we are talking about. We can also link them to damage or loss. And this is quite important because this will then bring us to other discussion on resilience when we talk about that. That means what kind of loss or damage are we expecting at each performance level? So here, 0% loss. Here, everything is gone. And here, somewhere in between. So that's another indicator that we can put along with this performance indicator. We can actually put other things here. For example, money. We can put life. We can put time. So there are many things that we can put on the scale, which is part of the resilience-based design. But anyway, coming back to the performance levels. So we have these 4 important levels that we should think about. How do we connect them to hazard or earthquake? These are independent, but a structure could be operational for a weak earthquake, and same structure may not be operational for a strong earthquake. So how do we link them to the earthquake level? And that's the next step. That means we link the hazards to the level of hazard and also the level of damage. So now we can say that, okay, at this point the structure is undamaged, and at this point the structure is just immediate occupancy, and it is life safety and collapse. And this then can be linked to the hazard level. We can say which hazard level are we talking about for these different levels, and that blue line is the structure's performance. So we can now look at the structure's performance against the indicators, against the hazard and the displacement and everything. So basically this is a way to connect the design decisions with the performance indicators, with the expected hazard levels. And this is really nice because now we are in a position to start talking to people in normal language and not necessarily only in engineering language. So this is another advantage. Now let me show you some important step. How do we actually link the hazard to the design decisions? Let's say there is a structure, simple one, is a frame here. And then there is the earthquake, that is the ground motion that we have measured, or we can measure the ground motions, or we expect a certain ground motion to come over there, and this can be determined through many ways, another subject that we will talk about when we talk about how. And then it can be converted into a response spectrum. And then, on the other end, we have the materials that we are going to use. We are going to use concrete, we are going to use steel. These are the strengths and these are the stress strain curves that we have from them. And this is the cross section that we are going to use, that is the amount of reinforcement we will put. So on one end we have the materials, on the other end we have the earthquake. How do we marry them? How do we connect them together so that if we change something here, we should know what will be the impact on the performance for that particular earthquake. Or if we have a certain earthquake, how do we make the decisions so the performance will be acceptable? That is the connection that we need to make. And the first connection is pushover curve, for example. There are other ways to do that. So for example, from here, from the cross-section, we can go to moment curvature. From moment curvature, we can go to moment rotation. From moment rotation, we can go to force displacement. From force displacement, we can go to the earthquake, the response spectrum, and then we scale them, put them on the same kind of scaling, and then we connect and we see where the performance point will meet. So that is the point where the earthquake and the structure's performance meet at a certain, and then we can see whether it is life safety, whether it is immediate occupancy or not, because these displacements are actually defined on the structure's performance curves, or the members curves. So that's how we can connect the design decisions with the earthquake, with the expected performance. And this whole process requires advanced modeling, advanced analysis. It cannot be done by traditional methods because it requires nonlinear modeling. It may require nonlinear dynamic analysis, and it definitely requires greater understanding of the actual structure that has been built. So that's the basic framework that we can use to do that. Once we have the framework, or we have the tools, the next important thing is that we define what are the hazard levels that we are going to check. What kind of earthquake are we going to talk about? And this should be in a human term that people can understand. so that when we communicate with the clients or with the public, they should be able to understand. We should not tell them, I'm going to design your structure for zone 4, which has no meaning for a person on the street. We should be able to tell them that we are going to design your structure for this kind of risk. The owner or the public and the engineer have to have a common dialogue or language. Currently, engineers are talking about deformations and ductility and concrete strength, and they're talking about things that clients do not understand, the public doesn't understand. What they understand is a certain risk to them. They understand a strong earthquake versus a weak earthquake, and so on, something that they can identify. An earthquake where the chairs are shaking, or an earthquake where the chairs are not shaking. That is how the public will see the earthquake. So we need to be able to bring them together. So one way is to define the earthquakes as frequent, occasional, rare, and very rare. So we say, okay, this is an earthquake that will come frequently, 50 years, every 50 years, or once in a lifetime earthquake, which is, in an earthquake scenario, this is a frequent earthquake. So that means your structure is likely to experience this earthquake during its lifetime. High probability it will come, and that's a frequent earthquake, that the kind of earthquake that comes quite a bit. Another earthquake is which come occasional. So this is about 225 years, every 200 years roughly it will come, once in every 200 years. So it's occasional. Then it is a rare earthquake, which is coming after every 450 years return period. And another one is a very rare, exceptional earthquake, which only comes after every 2,500 years. So now if you tell this to the client that you are talking about earthquake levels like this, they will understand that, okay, I am interested to design my structure only for frequent one because the structure is only a warehouse and there are no people there, so I don't mind, it's okay. But if it is a hospital, or if it's an emergency center, they will say, oh, I want to make sure that it survives even in the most rare earthquake, because this has to serve people. So then they can make a decision based on the severity of the earthquake with their building's usage and their expected performance. Now we are on talking in a language that people can understand. And then we bring these back and then we connect them to these levels. We call it service level assessment, and we call it collapse level assessment. So we have this, okay, this is the serviceability. Structure will be fine. If it's an hospital, it will continue to operate. It won't be shut down. And it's a collapse prevention. It won't collapse, but it will be damaged. So those are the two extremes. I think everybody knows about this strong earthquake in Japan, where the nuclear power plants were damaged. And the consequence of that damage is still going on after so many years. It's billions upon billions of dollars. And the whole country's economy was affected because of decision of this kind on that. Because a nuclear power plant is not supposed to crack even in extreme or most rare earthquakes. So this is where the building codes are sitting. The building codes are sitting in somewhere they call an arbitrary implicit design earthquake, which is about 450 years return, which is a rare earthquake. And that's in their mind, but they don't tell this to the public. They tell them, this is zone 2, zone 3, zone 4, or acceleration is like this, or ground, But this is the intent of the code, that it is a rare earthquake, and that's the basis of the design. But on this basis, they expect the structure to damage significantly. Life safety, yes, damage expected. But if you tell the client that your structure will be damaged severely, he's not going to like it. And you say, I follow the code, but please expect your structure to be damaged severely, I don't think any client is really going to like that statement. He said, what are you talking about? I'm spending a lot of money, and I'm paying you a fee, and you're telling me that my structure will be damaged severely after that earthquake. So to solve this problem, then the performance-based design investigates two more levels, one before and one after. One is service level earthquake. So then you say, okay, fine, if you want your structure to be completely serviceable, this is the earthquake that you should be checking it, which is the frequent one. So it will come once or maybe twice the lifetime of the structure, but your structure will be completely serviceable if you want that. And then, so this is one level of assessment that we can carry out. Second level of the assessment is we will make sure that it will not collapse for the most rare earthquake, So we check those two explicitly, and in between is not really necessary because this doesn't mean anything, but this means collapse prevention, this means serviceability. So the client can actually move these things around depending upon what they want. For a hospital, they can move the earthquake level to different locations and say, well, I want serviceable hospital even for this level, for example. Fine, the engineer should be saying, okay, fine, I can do that. But if you just design on the code, engineer has no answer whether your your building is more safe than less safe compared to other buildings. So that's the whole, I would say, summary of the performance-based design as far as earthquake is concerned, where the explicit evaluation beyond the code on 2 levels is done. This is still done, but we do that on top of that. So now the owner and engineer can sit on the table and have a meaningful conversation because they have come to the same language that they can now understand. So owner's question, will the structure be safe, which was my question for the first video last time. Can I use the building after the hazard? This is still tricky, but then based on the immediate level or the occupancy level, we can say yes and no because we have those 4 levels. So we can answer this question. How much will repair cost in case damage? We don't have the answer to that yet. And how long will it take to repair? We again don't have answer to that. Performance-based design does not answer these 2 questions. Resilience-based design answered those questions, which I mentioned as one of the last step in the discussion last time. So we will talk about those in another time. But for now, we can kind of answer those 2 questions. And the engineer is then free to choose the solutions. Once the client makes the decision here, then engineer is free to choose how to satisfy those requirements. It doesn't have to, she doesn't have to follow the code explicitly because code doesn't give that information. So engineer's responsibility is to prove that what the decision that she has made are actually going to be delivering what the client is expecting. And because this is such an advanced, a difficult job, a third party has to come in to make sure that the engineer is doing it right, because engineers' capabilities may vary. So one engineer may have greater understanding capability than the others. So how do we trust the engineer's capability? Because the client should be sure that engineers knows what they're doing. So a third party comes in, and that third party is actually 2 groups. One is the guidelines, other engineers who have developed the guidelines how to do this, and also a peer reviewer who actually has more experience than this engineer, and then checks the design and makes sure that, and agrees that, okay, this is fine. So the client has greater confidence level on what the engineer has done. So this kind of arrangement is what makes performance-based design possible and reliable, and at the same time it gives explicit evaluation that people need. So this is the overall framework of carrying out the performance-based design. And just to quickly go through operational level, what does it mean? It means negligible damage. It means everything is working, utilities are fine, and there's a less than 5% of replacement value. So damage will be, if there's any damage, it will just be cracking of the partition walls and so on. We will talk more about that at another time. And then immediate occupancy level, the building is safe to occupy but may not function completely. There could be some damage here and there, some portion may be damaged, those kind of things. So these levels are well understood now. And then we have the life safety level. The structure is damaged significantly. Losses could be as much as 30% of the cost, and extensive repair may be needed, but no life will be lost. And then collapse is that the building will have to be demolished or is already gone or cannot be repaired anymore. So that's another level that we can consider. So that's roughly the case. And then we can put them all together again on the structure's performance, and this blue curve can be determined through analysis. And when I say analysis, it requires advanced analysis. It requires nonlinear modeling. It requires dynamic as well, and maybe nonlinear dynamic together. So it is definitely a lot of work to do this, and a lot of understanding needs to be done to do this right and reliably. But once we do that, then we have the whole picture in front of us. How do we judge performance? The last part of the discussion. So now we have defined the performance levels. We have found a way to link them together. How do we check that this structure is going to be operational. What does it mean for a structural engineer? That is not for the client anymore. For the client, it means it's operational. But how do you calculate something and say, oh, this structure is going to be operational? You cannot just look at the results on a computer model and say, oh, this is going to be operational. There has to be certain numbers that you say, okay, this is between here to here is operational, here to here is not operational. And this has to be done at many levels. So this is now for the engineers to be able to prove that it is actually, the performance level is actually achieved. So there is a local and there's a global limit or range on everything that they calculate. So when you calculate some number, there is a local range for the beam and one end of the beam for moment, for shear, and there's a global range for the whole structure. So when we look at these local and global computational limits, then we can simply check our numbers against that, and then we can do some assessment. So before we do that, we have to see whether the structure is brittle or is non-brittle or ductile. This is very important because ductile things can deform a lot without collapsing. They give warning, so there's a different rules for that. If it's a brittle structure, as you know, it will collapse suddenly without warning, so that's a different rules for that. So we have to distinguish what is ductile, what is brittle. In each member, within that member, different actions could be ductile or brittle, and different locations could be brittle and ductile and so on. So we have to do that, and so this is a guideline. So whatever I'm saying is actually a guideline. This is not really the code. These are guidelines. So you say, okay, for column, this is the axial flexural is ductile, shear is brittle, and for shear wall, flexure is ductile, shear is brittle, and so on. And then we do what kind of behavior is expected, linear or non-linear. So based on that, you do the evaluation and you check the results. And then these are the curves that have been developed, which basically bring it back to what I showed you in the slide, where we have the material definition, which is the stress strain curve. So we can have the stress strain curve, can have a moment curvature curve, we can have a load deformation curve, and those curves, on those curves, we can put the lines which correspond to the same performance levels that we have for the structure. Immediate occupancy, collapse prevention, and so on. So everything is completely on the same scale, right from the structure to a particular cross-section or even a material. So then we say, okay, this is immediate occupancy, and this curve is not of the structure performance. This curve could be of a material, could be of a hinge, could be of a member. So now we have very, very consistent as well as uniform application of the performance indicators coming all the way from earthquake down to the members' behavior that we determine or the calculations that we do. And these are the checks that we perform. So this is and they all have the same sense. There's a deformation, there's a force. And so the deformation is on, so we link them together. It's always deformation versus force in this case. And then we can have the same one for secondary component. And you can see here, secondary components are allowed to break. This may be accepted structurally, but may not be accepted by the public. And that's where the resilience-based design comes in and say, okay, this is also something that we may have to talk about. Because if all the partition walls are damaged or all the ceilings are damaged, that's no good. Even the structure is standing, because the structure still has to be repaired a lot. So that's why these may also shift depending upon what the intent is. So now we come to almost the final measure, which is the demand capacity ratio. And demand capacity ratio basically shows finally a pass-fail indicator for a structural component or action or a member. And it shows that, okay, this is what we wanted, this is what we're getting, is this okay or not? So it's a yes, no kind of a question at that point. And then the DC ratio, demand capacity ratio, is if it is less than 1, we say is pass. If it is more than 1, we say, well, not really pass. 0.9, 0.1 is a judgment call, and some engineers can pass up to 1.2. Some engineers are very conservative, they will fail at 0.99. So it's a decision that people can make. And this is where the importance of structure, member, and so on will also come in. So the two types of demand capacity ratios, one is based on force for the brittle members, and one is force based on deformation for ductile members, and we combine them together. and we check both the demand capacity ratios in this case. And for these are various limits, acceptance criteria, and these have been developed. I don't need to go into the details. You can find these references quite easily in many places. And then for the maximum credible earthquake or a severe earthquake, the criteria could be different. So these are the limits. So the point is that now you have numbers here. So for example, rotation, 0.06 radian rotation limit. This is a number that engineers love to deal with. They see this thing, they calculate rotation, they check against it, it's fine, I'm done. But actually what they're doing is they are satisfying a certain performance indicator for that location, for a certain earthquake, for a certain risk. So the whole cycle is completed when they look at this number and they satisfy. And if you change something in the structure, this number will change. And if you change the earthquake, this number will change. So which means that now we have a relationship between design decision and the earthquake level and the final performance. It's not just that you follow something and you don't know what really happened. So it brings me back to what I said previously, that if you change the spacing of the stirrups in a column, you should see some change here in these numbers. So whether I should follow the code and use spacing of 4 inch or 100 millimeter, or I can do 175, as long as this is satisfied, 175 may be okay if you can demonstrate that 175 does not cross this limit here, which is corresponding to a certain performance level. So that's what the performance-based design is all about. So let me just conclude by saying that performance-based design and performance-based evaluation is a way to explicitly define the key performance indicators and to be able explicitly and reliably determine them and to satisfy them through design decisions. So 3 parts. First of all, you have the indicators, you are able to define them, you are able to compute them, and you are able to link them to your design decisions. So if you are able to do all of that, that means you are doing a performance-based design. Whether you know it or you don't know it, whether you call it like that or you don't call it like that, that is what performance-based design is all about. So I hope that this discussion will then lead us to the next discussion on how do we do that? How do we carry it out? Carry out what the performance-based design. This will get into a little bit more technical stuff, and we will see some of that. So we'll talk about when and how to conduct performance-based design, and finally, what are the benefits of doing this one. So thank you once again, and look forward to seeing you in the next talk.